Today's session we'll talk about Fourier series, uses of Fourier series, what are the different conditions under which Fourier series converge or exist. Then we'll look at some various problems in Fourier series after finding out what are the different types of expressing a Fourier series. So let's start, let us look at the PowerPoints now. Okay, what is a Fourier series? It is the representation of signals over a certain interval of time in terms of linear combinations of orthogonal functions is called as a Fourier series. Sometimes Fourier series is also called as a harmonic analysis, and one of the most important point to be remembered in Fourier series is Fourier series applicable only to periodic signals. So whenever you find a signal which is not periodic, then we can straight away say that the Fourier series does not exist for this. Next slide. Let us see the uses of Fourier series. As I have said, Fourier series is basically used to analyze periodic signals. The harmonic constant of the signal is analyzed again with the help of Fourier series. Fourier series can be applied to both continuous time signals and also discrete time signals. So whenever we have a system or a signal which is in continuous in time domain, then we can apply Fourier series. Similarly, even when the signal is in discrete time, Fourier series can also be applied to discrete time series also. Let us look at the basic conditions under which a Fourier series converge, or we also say these are the sufficient conditions for a Fourier series to exist. These are called as Dirichlet's conditions. Okay, there are around 4 of these conditions. Some of them are called as weak conditions, some of them are called as strong conditions. So when it is a strong condition, it means when this particular conditions are satisfied, then the Fourier series definitely converges for all values. When it is a weak condition, it means the Fourier series does exist, but it may not converge for all. So let us straight away look at the what are these Dirichlet conditions. The Dirichlet conditions, the convergence of the Fourier series of function is given by the Dirichlet conditions. Okay, and here I emphasize these conditions are sufficient conditions to be satisfied by a function x of t for its Fourier series representation within the interval t1, t2. As we have said, this is a periodic, so we must mention the time interval here. So time interval must be mentioned. So let us take the time interval as t1 and t2, then the Fourier series exists. Let us straight away look at what are these different conditions. Let us first talk about the first condition. Okay, the first condition says the function x of t is a single valued function of the variable t in the interval t1, t2. That means the function which is given, let us say x of t, must have only a single value at a given time. If it is not having a single value, then the Fourier series cannot exist. So let us see this on the board. Okay, now let us take a function like this. Okay, this is t, this is x of t. Let us say our function is like this. Now let us take a time t1. Okay, so for a time t1, what are the two values that can exist here? There are two values that can exist. One is this value. This is one value that can exist, and this is the second value which can exist. So what does the Fourier series first point says? The function must be single value. The function first Dirichlet condition says the function must be single valued function. So if I look at this particular function, what is there? For a single time there are two functions. So I cannot have a Fourier series described for this functions. So let us see what type of function will have a single value. Okay, let us draw another figure here. This again is t and this is x of t. Okay, so this is the function. Let us say at t1, what is the value? So this is a singular value. That means this signal is having only a singular value. That means Fourier series will exist for this, whereas the Fourier series does not exist for these type of functions. Okay, let us read that condition again so that you will remember this permanently. Shall I read? Yeah. The function x of t is a single valued function of the variable t in the interval t1 and t2. Okay, so this we have seen even on the board. We have seen two cases where a function is having more than one value, that is double value, and also we have seen another where it is having single value. So for a single value, the Fourier series does exist. Let us look at the second Dirichlet condition. It says the function x of t has a finite number of discontinuities in the interval t1 and t2, and each one of these discontinuities is finite. So what does it say? That means when I have a function x of t, it must have finite number of discontinuities. If the discontinuities are infinite, we cannot have a Fourier series described for it. Let us look at again an example on the board which indicates what is this discontinuity for which the discontinuities are finite and for which discontinuities are infinite. Let us look at that. Okay, let us take a case here. Let us say this is our case here. Okay, this is x of t. Okay, this is t here. When I look at this, see the discontinuities here. The discontinuities are extending like this. So there is no finite discontinuities. For this, I cannot write x of t. As I am not able to write x of t equation, the Fourier series cannot exist. We see a case where finite discontinuities are available. Let us take another case here. Okay, this is t. This is x of t. Look at this, there are finite number of discontinuities. That means I can write an equation for this. How can I write an equation for this? X of t can be written as, here t is nothing but t for us, here this can be written as x of t minus plus x of t plus by 2. So when I write this equation, I will get the value of x of t. See here t. At t 0 minus, there is a certain value. At t is equal to 0 plus, again a certain value. So we will take this those two cases, and when I take the average of value of this, I will get x of t here. So this is a case where you have finite discontinuities. This is where I cannot define the function because there are infinite discontinuities. So there is no Fourier series that exists for this. There is a Fourier series which exists for this type of cases where there is a finite number of discontinuities. This is about the second Dirichlet condition. Let us look at the third Dirichlet condition. This says that the function x of t has a finite number of maxima and minima in the interval of t1 and t2. That means given a function x of t in a certain period, it must have finite number of positive values or finite number of negative values. Suppose if we take the positive value as a maxima and the negative value as a minima, it must have a finite number of maxima and minima. If the maxima and minima are not finite, that means they are more than what we can count. That is, when we say that they are infinite, then the Fourier series does not exist. So let us look at this again with a certain suitable example on the board. So let us take a case here. Let us say my x of t is defined like this. Okay, now let us take a figure described like this. When I look at this particular figure, there is no way we can find out the number of maxima or minima in this case. Then suppose I have a graph like this. Let us say I have a graph like this. Okay, let us call this as plus a and this is minus a. This is x of t and this is t. So as you see here, we have a maxima and a minima which are finite. So Fourier series exists for this type of sequences, this type of graphs, whereas we cannot define a Fourier series for this type of cases where there is no maxima nor a proper minima is defined. The Dirichlet condition, fourth case. The function x of t is absolutely integrable over any period. That is, when I integrate between a certain limits x of t dt, the value must be less than infinity. So the Dirichlet conditions give us what are called as sufficient conditions. So if I am able to satisfy all these four cases or any one of these cases, then Fourier series will exist. Whether Fourier series will converge for all values or it converges only for a certain values, but still Fourier series can exist. So Dirichlet conditions must be taken, all four of them, and then we can find out whether a Fourier series exists or not. So these are defined as sufficient conditions. Next slide. Let us look at note, one important note. We call the condition 4 is known as the weak Dirichlet condition. That means if it is absolutely integrable, that means the value is less than infinity, is called as a weak Dirichlet condition. What do you mean by weak? It means if a function satisfies this weak Dirichlet condition, then the existence of the Fourier series is guaranteed, but the series may not converge at every point. So this is what I was saying since the beginning, that when I have a condition which is weak, Fourier series existence is guaranteed, whereas the convergence is not guaranteed. Okay, let us look at note 2, which gives us what is the strong condition. Note 2 says the conditions 2 and 3, that is, it must have finite discontinuities and also it must have finite minima and maxima. If these two conditions are satisfied, then you have a very strong satisfaction of Fourier series. That means the Fourier series also exists, whereas the convergence is also guaranteed at every point. Okay, just read again here. Conditions 2 and 3 are known as strong Dirichlet conditions. If these are satisfied, not only the existence of Fourier series is guaranteed, but also the convergence is guaranteed. A lot of questions are being asked based on Dirichlet conditions basically in GATE. So different questions, different types of waveforms are being given, and we are able to, or we are asked to find out which one satisfies or which one does not satisfy. In other words, we have to find out which waveforms that the Fourier series exists or which waveform Fourier series does not exist. Now let us see the expressions for Fourier series. Basically, a Fourier series is a set of harmonically related sine and cosine functions, that is sin n omega naught t and cos n omega naught t, where n is 0, 1, 2, forms a complex orthogonal set over an interval t0 to t0 plus t, where t is given by 2 pi by omega naught. Okay. Now let us see. X of t is basically written in terms of harmonically related sine and cosine functions. So we use the letter A for indicating the coefficients of the cosine function. B is used as coefficients for the sine function. So it means it is a addition, it is a harmonically related functions, isn't it? So x of t can be written as a sum of a0 plus a1 cos omega t plus a2 cos 2 omega t plus a3 cos 3 omega t plus so on up to a certain term, let us say n, and follows beyond n also, then followed by b, b1 sin omega t plus b2 sin 2 omega t plus b3 sin 3 omega t, so on. Okay. X of t is equal to a0, which is called the DC component, plus a1 cos omega naught t, a2 cos 2 omega naught t plus an cos n omega naught t plus b1 sin omega naught t plus b2 sin omega naught t. Like that you have n harmonics. That means the fundamental component omega naught, this is the second frequency component, and this is nth frequency component, similarly for a sine. So basically a Fourier series is the expression of a signal x of t in terms of an average value plus harmonic components of cosine plus harmonic components of sine wave. So this is in essence the expression for a Fourier series. That means this is basically a summation which is happening. So I can rewrite this equation as follows. So what I will do, we will take the DC component plus this is summation. Okay, summation, be very careful, we are starting with n is equal to 1. Why n is equal to 1? Because this is where we are starting. Okay, n is equal to 0 has resulted in a0 for cosine terms and 0 for sine terms. So we are just writing a0 here, and then this may go up to infinity. So this will be cos n omega naught t plus sin n omega naught t. So what is missing here? We have to write the coefficients here. So I am writing coefficient a here, and I am writing another coefficient here, which is b. So this is the complete expression for a Fourier series. You have a DC component for a summation of an cos n omega naught t plus bn sin omega naught t. So if we expand this, what happens? a1 when n is equal to 1, a2 when n is equal to, like that we can have up to infinity. So what is the time period? You can take a time period of t existing between t0 plus t, and it will be from t0. Okay, so this is the period which we are talking about. Okay, so this is a complete expression for a Fourier series which exists like this. So we all have to remember, I just tell you again once more, you have an a0 here, which is a DC component, average component, plus a summation, which is in essence the harmonic addition of sine and cosine terms. Harmonic addition starts from n is equal to 1 plus infinity. Okay, so this is the fundamental basic expression of a Fourier series. The expression that we have just written is called as a trigonometric Fourier series. It is called as a trigonometric Fourier series representation. So here we should have formulae which describe what is the way in which we calculate A naught, what is the way in which we calculate An, and what is the way in which we calculate Bn. Let us see in the PowerPoint now. So A naught is given by 1 by t, that is a period, integral t0 to t0 plus t x of t dt. So this A naught is called as the DC or average value, as I have already spoken to you. In the second one, how to calculate An? An is given by 2 by t integral. The limits are from t0 to t0 plus t, as we have described, x of t cos n omega naught t dt. When I integrate this, I will get the value of An. Similarly, how do I get Bn? Same almost. It is 2 by t integral t0 to t0 plus t x of t sin n omega naught t dt. Okay, let us write here. This is the what is called as the average value. Okay, and A0 is given by 1 by t integral t0 to t0 plus t, because this is what we have taken, x of t dt. So I will get this here. Now how do I get An? An is, I get like this. This is 2 by t t0 to t0 plus t x of t cos n omega naught t dt. So this will, I will get this An here. This is the coefficient of your cosine terms. And how do I get Bn? Similarly, Bn you can get like this, almost same. It's very easy to remember this formula. T0 to t0 plus t x of t sin n omega naught t dt. So we have seen very important formulae on the board now. They are all written together so that you remember them permanently. We have expressed x of t in terms of a summation here, and also we have seen the formulae to calculate A naught, that is average value, An and Bn. Let us see another way of representation of Fourier series. The first one is trigonometrical Fourier series. Now let us see how or what are the different ways in which we can express the Fourier series. The second one is called as the harmonic form or polar form, and the formula is as follows. X of t is equal to C naught plus summation n is equal to 1 to infinity Cn of n omega naught t minus phi n, where omega naught is 2 pi t, is called as a harmonic form of Fourier series. Where again let us compare this with the earlier form which we have written. It says C naught is again a DC component in this, and then Cn n omega naught minus phi n is the nth harmonic component of x of t. And if I take n is equal to 1, this becomes a fundamental component, and Cn is the harmonic amplitudes, and phi n is called as the phase angle or the spectral phase. This is a very important slide where a lot of terms we are going to learn in this. X of t is equal to C naught plus a summation n is equal to 1 to infinity Cn n omega naught t minus phi n. So there are different components which you can look at. One is called as a Cn component, and there is a phase angle component which is phi n. Okay. So here C0 again same as the earlier case is again a DC or average value of the signal, and Cn will give you the harmonic component of the signal. If I say Cn of n omega naught t minus phi n will give me the nth harmonic component, and if n is equal to 1, this gives me the fundamental component. Similarly, you have a phase angle which is phi n. Let us see this. Now this is the equation. We have C naught plus summation Cn n omega naught to minus phi n, where omega naught is how much here? Omega naught, we can write this as equal to 2 pi by t. That's always, we know that. So what is it we are doing? We are having here some component. This is called as the DC or average value. Okay. This is called as the nth harmonic component. Okay. Now if I let us say I put n is equal to 1, then this becomes C1 omega naught t minus phi. This is the fundamental component. Okay, this is the fundamental component. So this you should remember. Okay, this C naught is the DC as the average value, and this is the nth harmonic components, and when n is equal to 1, this becomes the fundamental. What are the Cn here? Cn exclusively is the amplitude of the harmonic components. You have a harmonic component which is present, and this gives me what is the amplitude of it. So this Cn basically gives me an idea what is the strength or what is the amplitude of the different harmonic components starting from a fundamental components. Whereas this will give me the phase angle. This is also called as a spectral phase. So this phi is the phase angle of your signal, and it is also called as a spectral phase. And the second form we have seen in terms of C, C0, Cn and all those things, isn't it? So there must be a relationship between the first one and the second one. So what is the relation? Let us see this. So we have the coefficient C0, Cn and phi n, and how are these related to what already we know, A0, An and Bn. So at the outset we can write down C0 is equal to A0. C0 is an average component or DC component, and A0 also is average component, DC component. So both of them are now. So it's simple. C0, whatever is the value for A0 is equal to C0, or what are the value of C0 is equal to A0. That's one point. Then the second comes, how do I calculate the coefficient of different harmonic components, Cn. So that is related to An and Bn. If you see the earlier form, in the earlier form, An is a coefficient of cosine terms and Bn is the coefficient of sine terms. Now if I square them and take a square root of An square plus Bn square, that will give me the value of Cn. Then comes what is the phase angle or the spectral phase. So phi n is given as tan inverse of Bn by An. That is the coefficient of the sine component divided by the coefficient of the cosine component. If I take the tan inverse of it, I will get the phase angle phi n, which is in the case of a polar form or also called as a harmonic form. We are looking at a third form, which is called as a complex exponential Fourier series. Let us see how we can express this. This is considered to be the general form and is a more compact form, and this is the most extensively used in communication theory. So as an electronics engineers, what we have to see is what is the convenience, how best we can use this type of form. The earlier two forms are oriented towards mathematics more, whereas this seems to be in a very compact form and is easily related to all communication theories. So we use this complex exponential series for our case here. Let us see the formula. Here the expression x of t is written in different components called as f for convenience here, because we don't want to confuse with the earlier case. X of t is equal to f0 plus f1 e to the power of j omega naught t, that is the first term, that is a fundamental term again. Then comes f1 e to the power of j2 omega naught t, so on, of 10 components, and goes on. The positive side of it. Then the negative side, that means on the left hand side also this exists. So this will be f minus 1 of e to the power of minus j omega naught t plus f minus 2 e to the power of minus j 2 omega naught t, and so on. Now one very significant feature I want to tell you now is, if you look at this type of formula, complex exponential Fourier series, and the earlier cases, remember the summation earlier was done only from 1 to infinity. That means if I draw the series frequency spectrum for the earlier ones, what happens? They exist only on the right hand side. Whereas this type of function where you see here, it exists from minus infinity to plus infinity. We see it is f0 plus f1, f2, f3 up to f infinity, up to the infinity, and also it's from minus 1, minus 2, minus 3, minus 4, it's going up to minus infinity. That means the summation here is basically from minus infinity to plus infinity. That means if I draw the spectrum of this Fourier series, it exists on both sides of the 0. That means there is a negative side spectrum, there is a positive side spectrum. This is a very important point which you all should remember. Let us see the complex exponential series representation. As I said, this is from minus infinity to plus infinity. If you remember the earlier summation was only from n is equal to 1 to infinity, isn't it? So the difference between this and this is, if I take it on an axis, this type of representation is only on this side. So it exists only on this side. Whereas if I draw the spectrum of this, what happens here is, not only does it exist here, it also exists on this side, because the value of n is from minus infinity to 0, then from 0 to plus infinity. So it is a function which exists on both sides of the spectrum. Now this is, let me just read the formula. It is a summation of n is equal to minus infinity plus infinity. There is a coefficient again fn, and then it is exponential addition. It is e to the power of jn omega naught t. That's why it's called as a complex exponential series. Here we express the whole Fourier series in this type of form. So what is Fn here? Fn again is given by 1 by t, t0 plus t0 plus t, x of t e to the power of minus jn omega naught t. So this is the second wave expression. And one important difference which always I have told you, you must remember, is the earlier trigonometric and harmonic or polar series representation is only on one side, whereas this type of expression is on both sides. Now let us see the various relationship between the three forms of Fourier series which you have seen. That means A0, An, Bn. Then we have seen Cn, Phi n, C0. We have already seen those relationships. Now let us see how this F's and A's, B's are related. First point, A0 is equal to F0, right? Second, A0 is equal to Fn plus f of minus n. Bn is equal to j of f of n minus f of minus n. Okay, this is one side relation. Then also F0 is equal to A0, and Fn, given An and Bn, I could calculate Fn also. How do I get that? Fn is equal to half of An minus jBn. F of minus n is equal to half of An plus jBn. So remember all these formulae. These formulae are very important. When given in one form, you can transform them into another form. Next. The next few slides we will look at recollect all these important formulae which I have put together so that they will be very useful when we are preparing for some exams. Okay. Let us see these important formulae. The first one is the expression of Fourier series in the form of what is called as a trigonometric, or is also called as a sinusoidal Fourier series. As you see here, x of t consists of A0 plus summation which starts from n is equal to 1 to infinity, An cos n omega naught t plus Bn sin n omega naught t for a certain period, where A0 is again given by 1 by t within the integration within the limits x of t dt. An is again given by 2 by t integration within the period x of t cos of n omega naught t dt. Similarly, Bn is equal to 2 by t integral within the limits x of t sin n omega naught t dt. Next slide. Then how do I represent in polar form or harmonic form of the Fourier series? So here the difference is, again we use a word, we use the letters C0 and Cn in terms of other things. So it is again the same here. How does it look like? X of t again can be expressed in terms of C0 plus summation n is equal to 1 to infinity Cn of n omega naught t minus phi n. So the introduction of three new terms here, C0, Cn and omega naught. What is all this? We have seen C0 is again average value which is equal to A0, and Cn is the coefficient of the nth harmonic component is equal to square root of n square plus bn square. Then the phi n is the phase angle, is the spectral phase of the Fourier series. It is given by tan inverse of Bn by An. Then comes the third form, which is called as a complex Fourier series, where x of t is again represented by summation n is equal to minus infinity to plus infinity Cn. Okay, here we use Fn in terms of Fn in place of Cn. So it is x of t is equal to summation of n is equal to minus infinity to plus infinity Fn e to the power of jn omega naught t. Okay, that is, we are going to express complex exponential Fourier series in terms of all exponential components with a certain amplitude, which is Cn. Okay, or which is, which is Fn, where Fn is given by 1 by t integral within the limits x of t e to the power of minus j n omega naught t dt. So this is the third expression. Now I want all of you to go through this quickly. We have already done this, so just see how it exists. We all said that A0 is equal to F0 and An is equal to Fn plus Fn, f of minus n, Bn is equal to j of Fn minus f of minus n. Then f naught is equal to a naught, Fn is equal to half An minus jBn, f of minus n is equal to half An plus jBn. Then all this formula. So this we have put together all this because sometimes in GATE exams the relations are being asked. So you have to remember all these equations. Next. Now let us see some serious questions here, object type questions. We look at these questions. We try to look at them, and most of the first few questions are based on our understanding, the conceptual understanding, and also our remembering power, how we have remembered the formula which you have written so far. Sometimes these formulae are being asked directly in the exam, so we should not lose those marks. So let us start with the first question. The first question goes like this. The exponential Fourier series representation of a signal f of t over the interval t0 plus t is given by. So now we have already seen how we can express in exponential terms. So what is the answer here? Just think for a while. Okay, so let us look at the first case, n is equal to minus infinity plus infinity Cn a to the power of g n omega naught t, isn't it? So when we already remember the earlier cases, we know the answer is this. But if you look at the others also, you can see how best you will be confused. If you are not sure, then we will be confused by the presence of B, C and D. Okay. The basic problem with the second one was, if you see except everything, the summation is totally wrong. Okay, summation what we are doing is wrong, so it cannot be correct. The third one is, again there is a negative sign which is not true, and the fourth one, there is no exponential component at all in D. So what is the correct answer? The correct answer is A, which is nothing but summation n is equal to minus infinity plus infinity Cn a to the power of j n omega naught t. See how important you remember what are the terms under which summation is taking place. So this is the first question for you. So this is analysis which we have done, but in fact during exam you will not find so much time, but once you are sure about the correct formula, then you can just tick it. But before ticking, actually just look at what are the other options given, because there will be a lot of confusion that actually creeps in because the type of choices are given. So you should be very careful. The second question. The trigonometric Fourier series representation of a signal x of t over the interval t0 to t0 plus t is given by. The options are as follows. A0 plus summation n is equal to 1 to infinity an sin n omega naught t plus bn cos n omega naught t. Let us see the second option. B, A0 plus n is equal to 1 to infinity an cos n omega naught t plus bn sin n omega naught t. Let us look at the third option. C, A0 plus summation n is equal to 1 to infinity an cos n omega naught t. Then look at the final choice, that is D, A0 plus summation n is equal to 1 to infinity bn sin n omega naught t. Now let us see this. This is a simple problem where we should not lose it. If you remember the formula correctly, you can directly go at it. Also, if you remember what a Fourier series is, you can correctly take the answer. Here, if you remember what we have written earlier, the expression, we have used the letter A0 for mentioning the average value, and an has been specifically taken to represent the coefficients of the cosine term, and bn we have taken to represent the coefficients of the sine term. Okay, and also we have said that Fourier series is a combination of an average term plus a cosine term plus a sine term. So if you look at all the options, the first option is eliminated because here A0 is correctly mentioned, whereas the coefficient A is wrongly mentioned as the coefficient for a sine term. In fact, it is the cosine term. So the first one is eliminated. When you come to the second term is perfectly correct because A0 is there, that is average value. Then you have an, which is the coefficient of cosine term, that is mentioned clearly, and then bn is mentioned as the coefficient of sine term. The another thing which you have to look at here is the summation. The summation is again correct. It is from plus 1, that is n is equal to 1 to infinity. So it is perfect. When you look at C and D, they are automatically eliminated because already we have chosen the correct answer is B. But in spite of that, let us look at what is the deficiency in choice C and what is the deficiency in choice D. If you look at choice C, we are missing the sine term, and in choice D, we are significantly missing the cosine term. So it cannot be a Fourier series. So the answer is B. The third question is, the exponential Fourier series coefficient Fn is given by. Okay, there are 4 choices given, but I suggest, if you remember the earlier formula, we can in fact take this question even in the absence of the choices. But anyway, choices are given, let us see those choices. The first choice A is 1 by t integral t0 to t0 plus t f of t e to the power of jn omega naught t dt. Okay, that is first choice. Second choice is 1 by 2t t0 to t0 plus t f of t dt. Third choice is 1 by t integral t0 to t0 plus t f of t e to the power of minus jn omega naught t dt. The final choice is t0 to t0 plus t mod of f of t whole square dt. Okay, if you look at the process of elimination, we can straight away eliminate two choices. One choice where it talks about 1 by 2t, that can be removed directly, and the third one where there is no period mentioned, so that can be eliminated. Now the formula now lies between whether it is f of t integral 1 by t integral t0 plus t f of t, is it e to the power of j exponential which is positive or exponential which is negative. So the answer is the C. What does C say? It says 1 by t integral f of t. Okay, the integration limits are t0 to t0 plus t, f of t e to the power of minus j n omega naught t dt. So this is very important. So if you look at, if you are not well prepared, then you will be always have a doubt between whether it is plus or minus. That is going to be very fatal sometimes, because if you don't remember, you lose 1 mark or whatever the marks assigned to this, just because you have failed to understand whether it is positive or negative. So if you practice a little, if you remember this, then this will be a cakewalk for you. Okay, so the answer is C. Nice. Let us see the fourth question. The fourth question says, in the trigonometric Fourier series representation of a signal, f of t is equal to c0 plus summation n is equal to 1 to infinity Cn cos n omega naught t minus phi n. Okay, this is a trigonometric series for its representation, but is also called as a harmonic polar series representation. In effect, this is a offshoot of a trigonometric Fourier series. So the formula is given. So what does it say? It says f of t is equal to c0 plus n is equal to 1 to infinity Cn cos n omega naught t minus phi n. As we have seen earlier, there's different names given to different components which are used here. We have c0, we have Cn, we have phi n, and all this. Now the question is, what is Cn called? The choices are A, spectral amplitude; B, it is called spectral phase; C, it is called frequency; D, it is called angular frequency. Okay. So now if you look at this problem, it's simple again. If you remember the earlier ones, what we have studied was nice. But if you look at this formula, Cn actually happens to be a sort of coefficient or amplitude, isn't it? So the answer is A. It is called as spectral amplitude. Okay, we look at a similar question, that is next question, fifth question, which is almost, we are trying to test your understanding and your concepts, whether you remember your formulae which is given so far correctly or not. Because we are just looking at a Fourier series now. Tomorrow we have a lot of other things coming up. So remembering each time, everything will be difficult. So remember them whenever they come to you, and remember them for long time. So this plus the next formula plus next formula, all this formula you must be able to understand. Let us see the fifth question. In the trigonometric Fourier series representation of a signal, f of t is equal to Cn plus summation n is equal to 1 to infinity Cn cos n omega naught t minus phi n. What is phi n called as? The choices are A, phi n is called the spectral amplitude; B, phi n is called spectral phase; C, phi n is called frequency; D, phi n is called as the angular frequency. So the answer is phi n is called the spectral phase. Phi n is called the spectral phase, and the answer is choice B. Let us go to the next question. Sixth question. In the trigonometric Fourier series representation of a signal, A0 or C0 is called as what? Because we have seen two types of trigonometric Fourier series representation. One is where we have used A0 and the other where we have used C0. Now what is this called? The choices are as follows. A, it's called RMS value; B, it is called as average value; C, it is called as peak value; and D, it is called as a mean square value. Okay. So in the whole session we have been talking a lot about A0, C0. We call it as a average value, that is B. So the answer is B. Now let us look at the seventh question. The seventh question is like this. In terms of trigonometric Fourier coefficients is, the choice as follows. Fn is equal to, the first choice A, Fn is equal to half An minus jbn. B, Fn is equal to half An plus jbn. C, Fn is equal to An minus JBN. D, Fn is equal to An plus JBN. And the answer is Fn is equal to half An minus JBN. Let us see the 8th question. The trigonometric Fourier series representation, or talking about an even function. Of an even function consists of A, cosine terms, B, sine terms, C, both cosine and sine, that is both A and B, and D, none. So, even function, as you are all aware, x of t is equal to x of minus t, that is an even term. Okay. So, let us see what are the components present in this case. If you identify the type of function given, you need not calculate all of them and prove later at the end of the day that it consists of only cosine terms. But once we identify that a particular term is only even terms, then rest assured that there are no sine terms present in it. That is, all the summation related to sine, Bn sin omega naught, n omega naught does not exist. It is only cosine terms. Let us look at the next question, that is the 9th question for us. The 9th question is as follows. The trigonometric Fourier series representation of an odd function consists of. The choices are A, cosine terms only, B, sine terms only, C, both cosine terms and sine terms, D, none of the above. Okay, and the answer is only sine terms. Okay, here we should be very careful, because this is a practice session, this is a theory class where we are teaching you. These two questions, that is the earlier question, this question, have come on the same time. That means even we have only cosine, odd we have only sine. But invariably these two questions are not asked simultaneously. So you should be very careful, and remember that for even functions, for Fourier series, only cosine terms exist, and for odd we have only sine terms that are present. So these two must be remembered in isolation, not in relation with each of them. Let us look at the 10th question. The trigonometric Fourier series representation of a function with half wave symmetry consists of cosine terms only, sine terms only odd harmonics, only even harmonics. Let us see the answer, and the answer is it consists of only odd harmonics. So here in your Fourier series, n must be odd.